are the slides changing? I see one person nodding.
Yeah,
Yeah,
you
I
can
see one
nod, or
person.
you can always
Yeah,
do a little bit of that
yeah, I'm
if you
seeing
do
seeing
if it's
positive reinforcement. So
yeah,
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 awesome.
cool.
Okay, cool. I think we're good to go then.
We're ready to start. Okay, great. Well, let's get rolling. Welcome everybody. AVAR 2020. This is our third pre-conference event, and thank you all for showing up. As I mentioned earlier, we are in what Altspace calls front row. So if we get more people than can fit in one room, they spill over into another room and they won't know it. Hopefully everything is seamless. Um, my name is Lawrence Schwedler. I'm the program director of DigiPen's music and sound design programs. Today's panel or presentation is by the Epic audio team. Aaron McLaren is the lead audio programmer for Epic Games, and he and his team are going to present a presentation on Soundfield Submixes in Unreal, an extensible system for spatial audio. Aaron McLaren, just briefly, I don't have bios on everyone. I won't go into great detail, but he's an amazing guy. I've known him for a number of years now. He's been the lead audio programmer of Epic since 2015, where he has led the development of new multi-platform audio renderer, which is now shipped on all 7 platforms for Fortnite. Or actually, I think there's more actually, right, Aaron? It's more than 7? Or is
7
it 7?
now.
Oh, I got it right.
It's
I got it
growing.
right. Okay, only 7 platforms, right? He got his start in the game industry as one of the composers of the procedural music in Max's Spore. He's worked with Brian Eno, and later on Dead Space 2. He was one of the first technical sound designers at EA. I don't have an introduction for Ethan Geller, who's actually going to be do a lot of the presentation. So Ethan, my apologies. Again, this is all
Oh,
a
it's all
little
good.
bit bleeding edge, but for real, when we do this again, I'll be able to say a little bit more about your background too, and the other folks on the team. But I think I'm going to shut up and get off stage, and everybody clap hands and welcome Ethan Geller, Aaron McLaren, and wait, keep clapping, Max Hayes and Phil Pop of Epic Games.
If Lawrence, if you'd like, I can do a quick intro for these guys
Yes,
that are
please.
here. So Ethan joined us about 3 years ago now at Epic. Before that, he was at Dolby, and then before that, he was at Sony. So he's sort of one of my whizzes on the team that can kind of do anything as a DSP expert and has some great ideas. He went to school at Stanford at the Karma program. Phil and I go back a really long way. We both went to school together at UCSB in the Media Arts and Technology program. I guess like 10, 11 years ago now. Phil went off into a career outside of games, doing some really cool stuff with music information retrieval, which is a whole other field. So a lot of heavy DSP chops, machine learning, that kind of thing. And so Phil is sort of the wizard on the team with arcane chops in DSP land. And Max is a recent DigiPen grad. He started with us as an intern, and he has been sort of a rock star, um, jumping straight into some really cool features. And so Ethan and Max are listed as the co-presenters here, even though I think Ethan is doing the main talking, primarily because Ethan and Max work together quite a bit on this aspect of the feature. And so we're all here for Q&A at the end. Thanks a lot. Take it away, Ethan.
Sure, sure. Yeah, it's definitely worth noting that even though I'll probably be talking most, this was totally a collaborative effort. So yeah, thanks for that intro. Cool. Yeah, so this is about Soundfield submixes in Unreal. I'm going to talk a little bit about what Soundfield submixes actually are, what submixes are in Unreal, and how they solve some pretty complex problems in spatial audio, right? So kind of the main gist and the outline of this talk, last time I rehearsed it, I clocked it around 45, 50 minutes maybe. 50 minutes if I ramble too much. But we're going to talk a little bit about how audio spatialization plugins have worked in the engine and how they've been implemented. And, some applications of that with real spatialization plugins and how they sometimes had some kind of difficult topologies to express in the Unreal Engine and to reconcile with existing UX flows and existing sound design tools that sound designers were familiar with. And then we're going to talk about Soundfield submixes and how those are an approach to solve a lot of those problems. Right? Cool. So yeah, let's start with just how audio spatialization plugins have worked in the engine, right? So previously, we only had one way to do audio spatialization. It was called audio spatialization plugins. And essentially, the workflow for it was a sound designer would enable a plugin, be it Oculus Audio, Resonance Audio, etc. And you would select for a single platform, here is my spatialization plugin for this platform for this project, right? So for this game, we are going to use Resonance Audio for Windows or iOS, etc., etc. And then after that, right, we have a system called attenuation settings that is actually more of a generalized grab bag of pretty much all the ways that audio gets spatialized from a single source, sent to reverb, et cetera, et cetera. And in that, you could opt sources into using either our traditional padding method or into that spatialization plugin that you chose, right? I'm going to skip this slide because I think it's probably a little difficult to read. But essentially, when you implemented a spatial audio plugin, there was a very specific methodology and interface that we asked you to implement. And it basically said, hey, every new source that starts playing in the world, we are going to call your spatialization plugin, and we are going to give you an interleaved float buffer, typically monaural, although afterwards we added support for multiple channels if your spatialization plugin supported spatialization multi-channel audio. And we would give you some positional information, right? What's the listener's current world rotation, right? What is the relative transform of this source compared to the listener? And what we'd always expect is that you give us stereo audio as an output from that spatialization plugin. And then you may have a question about reverb, acoustics, et cetera, et cetera. And we had a very similar plugin system for reverb that we had for spatialization, where essentially a reverb plugin could get similar per source callbacks. So if you wanted to do individual acoustic processing for individual sources, you could do that. But additionally, you could create what we call a submix effect, which would apply processing to the mixdown of multiple sources that would get sent to reverb. We have an existing workflow that works fairly well for telling individual sources how they're going to behave and how they're going to send audio to the reverb submix, typically as a function of distance. So for example, you could have something where, oh, the source, as it's moving further away, we are sending more of its output audio to the reverb submix, and thus we get sort of a more reverberant feel from the source. And that kind of gets us to an additional Unreal feature that is really cool that Aaron implemented, and it works quite well. It's called the submix graph. And this is essentially the way that you express how sources get downmixed to what we call submixes. Submixes are basically just downmixes of multiple sources. And you could, apply DSP effects to those submixes. So we have a special submix called reverb submix that has all reverb processing of downmixed audio. And you could also route those submixes, right? We have this really nice sort of graph where you kind of choose your topology, right? You could have, oh, I'm going to send some audio to this submix, do some sort of effects work, spatialization, distortion, what have you. And then maybe send that to a different submix that does maybe a final dynamics pass, et cetera, et cetera. So one more feature that we'll talk about before we move on is how ambisonics have worked previously. And this was something that was kind of extended from the original spatialization plugin. And we basically said, if a spatialization plugin supports ambisonics decoding, well, we'll just utilize that, right? So, for example, if you enabled Google Resonance, we would create an implicit ambisonics submix, mix down all ambisonics sources to that, and then just to ask Resonance, hey, can you decode this ambisonic stream to these listener positions? So I think the million-dollar question for this is how well do all these work together, right? How do these kind of glue together into a singular cohesive workflow for sound designers, right? And the answer is kind of that it depends on the spatialization plugin, right? So we did have per source HRTF renderers, right? Oculus Audio has an implementation that allows for per source processing, where you know, for each individual source, you're essentially running two filters, right, for your left ear and right ear, and those are interpolated HRTFs. And you're getting back stereo audio, binaural stereo audio, for each individual source. And that's great because that's the way that the interface is designed, and then we can send that audio to submixes however the sound designer chooses to implement the topology of their sound design setup, right? However, we do have other spatial audio plugins that have slightly more complex topologies, right? So a clear limitation of per source HRTF renderers is that they don't scale very well, right? It's if you have one source being spatialized, that's two filters, right? And then if you have two, all of a sudden you're doubling your cost, right? We have this linear scaling of computational expense. So a lot of HRTF solutions use some intermediate representation, typically ambisonics, right? So something like Google Resonance says, okay, for each source that you have, we are going to encode that into ambisonics and mix that into an ambisonics bed, right? And then the actual HRTF spatialization is done on the decoded output of specific positions from that ambisonics bed, right? So this is great because regardless of whether you have one source or 32 sources, the actual HRTF processing is fixed cost, right? And that's typically for these HRTF solutions your computational bottleneck, right? And this is also really great for solutions like Resonance because you can do your acoustic sim or your reverb on that ambisonics Soundfield representation, right? Rather than having to think about some way to do processing on each source or on a downmixed sort of 2D channel bed for stereo 5.1, etc. And kind of the last category of HRTF spatializer that we have is external spatializers, right? You might be familiar with, Sony has talked fairly openly about their hardware HRTF spatializer, and there are similar hardware spatialization tools out there in the world. But most often the way that these work is you send source audio with a specific position and some metadata around like directivity, et cetera, to that hardware spatializer, and they output their audio directly to the user, right? Directly to the DAC. We don't get that audio back in any way, shape, or form, which is fine for a lot of use cases, right? But it's challenging to reconcile this with Unreal Submix Graph, and we'll talk about that a little bit here, because this is kind of the main issue that we're trying to tackle here, right? Is where we have a setup that's well designed for implementing per source renderers because we can just send the output of each individual source to the Submix graph. However, for stuff like Google Resonance, for example, it has a spatialization plugin and a reverb plugin, and those have to operate on the same ambisonics bed. So ostensibly, they both have to be enabled, and Resonance kind of has to pass audio from the spatialization plugin to the reverb plugin. And by doing that, right, they essentially output silence for each individual source, which kind of breaks a contract with our Submix graph, right? A sound designer may be sending source audio from Resonance spatialized source directly to a Submix output, and it might not be getting there. We do have systems for Submix sends that can happen pre-spatialization, which is usually how folks work around that, and that works quite well. But the main output is still out of the reverb plugin, ostensibly for stuff like Google Resonance. And finally, for these external hardware sends that we talked about, those are just fundamentally incompatible with our Submix graph, right? We can still do that thing where we send Submix sends for effects previous to when we send the source's audio to a spatialization plugin, but the actual output is going to be zeroed, and they're kind of fire forget situation, right? They're not going to send any audio out to our Submix graph. So the result is these kind of implicit behaviors that tend to confuse sound designers when they're working with spatial audio plugins, because we're not surfacing to them the actual topology of these really complex spatial audio solutions, right? So we had to kind of go back to the drawing board a little bit and kind of redesign our thinking around audio spatialization as a concept, right? And if you break down audio spatialization to its fundamental core parts, right, we've kind of got two parts of audio spatialization typically, right? You have capturing as much spatial information from independent sources in space with some metadata perhaps attached to them to some intermediate representation, right? That might be ambisonics, it might be a virtual speaker array, et cetera, et cetera. But eventually you take that intermediate representation and you translate it to audio for speakers at independent physical locations eventually, right? And if you think about it, this is actually fairly similar problem space to microphone arrays and the way microphone arrays work. Dan Reynolds, a technical sound designer on our team, and a great person to talk to, was kind of the person that kind of opened my mind to this concept, right, of thinking of audio spatialization from the perspective of challenges that recording engineers and audio engineers that work with microphone arrays typically deal with. So let's kind of work with that metaphor a little bit. Let's think about these channel formats, these intermediate spatial representations as microphone arrays, and try to work with them from the least amount of spatial information that we can capture to the most amount, right? So of course, let's start with a mono submix, right? A single channel of audio. This is the least possible amount of spatial information you can get in a downmix of multiple sources, right? So this is kind of similar to kind of just going out into the world of your game and just placing an omni microphone just in the world, right? And, you know, I like this diagram from our documentation because if you imagine a bird kind of flying past your microphone, it might get louder as it approaches and it might be quieter as it goes away. But beyond that, we don't have any spatial information, spatial cues that we can really derive from this single microphone, right? However, if we just add one more omnidirectional microphone, one for our left channel and one for our right channel, suddenly we have one vector of spatial information, right? You're able to say, hey, this bird is flying from the right side to the left side of the player, and as they are flying in that direction, the right channel is getting quieter, the left channel is getting louder. And all of a sudden, we have some element of spatialization, right? We could tell how far to the right or to the left this bird is. So already this is eons better than just a mono microphone. Which brings us naturally to surround sound setups, right? Where you have a 5.1 or a 7.1 setup. And with these, you have two vectors, right? And you have much more granularity in your spatial representation because we have these surround channels, right? These channels behind us that will give us front versus rear spatial cues for the audio, right? And if you think about downmixing to 5.1 or 7.1, this is kind of akin to placing an omni microphone with some pickup pattern that may either have linear fall off or power-related fall off, and placing each of those omni microphones at each of these speaker locales, right? But the problem that we get here is that we don't have any elevational information with the 5.1 or 7.1 setup, right? Which is where ambisonics kind of came in as a great fit for a lot of spatial audio solutions, right? Because it's ambisonics, if you're not familiar with it, it's kind of projecting a sound field onto the surface of a sphere, ostensibly by doing a spherical harmonic decomposition. You may have worked with ambisonics microphones in the real world, and they do exist, and they do a pretty good job of capturing spatial information from a single place, a single point in your sound field, right? So this gives us azimuth, right? This gives us left, right, front versus rear. It gives us elevation. It gives us whether an individual source is above us or below us. It does not give us depth or volume, right? So we don't have anything in the sound field representation that will give us like whether an individual source is 4 feet away or 2 feet away, given a specific angle, right? But a lot of spatial audio solutions downmix to a virtual speaker array, right? They can, this is great because they can choose as many channels as they want. They can downmix to as many channels as they want. You can have a 12 speaker virtual speaker array. You can have 16, 24, however many you need. And although it may be hard to conceptualize this as a microphone array, they do exist This is one of my favorite Karma projects to look at from, I think it was 6 or 7 years ago. But Jonathan Abel, Jonathan Huberth, and a couple other folks led this microphone technology, like acoustics project, where they went to Chevin and took this microphone cluster. You can kind of see these kind of dangly bits on these metal rods, right? And each of those is an individual cardioid microphone. And essentially, below those microphones, they placed 4 speakers and ran a couple of triangulations to get the position of each of those microphones. And by doing that, they had a cluster of microphones that they had the positions for, and were able to get a pretty decent spatial representation of the space using that. So virtual speaker arrays are very useful for a lot of audio spatialization solutions, right? But the problem is that, you can kind of set up 16 speakers, right? And you'll evenly space them out. But there may be a lot of sources on the left side, and you're doing a lot of work with your virtual speakers on the right side that you may not be getting a lot of gain from in terms of spatial granularity, right? Which is where a lot of solutions do stuff like dynamic clustering, right? So you can imagine a virtual speaker array, except each speaker is moving dynamically to sort of capture the centroid of many sources, right? So you can have, here's like 16 sources that exist out here, slightly to my right, and I've downmixed them to 3 individual sources, right? And this is great because you can have largely fixed cost systems by identifying those centroids, right? You can say, I'm always going to downmix to 5 or 6 dynamic locations at any given time, and then operate on those. It's hard to find kind of an analogous microphone array to this, but if you think about large microphone arrays that do beamforming, actually structural sensors on bridges kind of operate similarly to this, where you will have a bunch of structural sensors along a bridge, and then as a car is moving past that bridge, there's beamforming to try to track the location of that car and to try to essentially track the vibrations from that car out to these independent structural sensors. There's also stuff like conference microphones, right, where conference room microphone arrays, where it's like, we've got 16 microphones, right, in an array here, and then we try to direct that microphone array towards a specific speaker using something like a naive delay and sum beamformer, what have you, right? But this actually adds an interesting wrinkle to our Soundfield representation problem, because with all of our previous situations, we could kind of infer speaker locations and any information we needed without having to add any metadata to the audio stream, right? If you think about a 5.1 audio buffer, as long as we can infer there's 6 channels in this, and we know that our engine uses a fixed order, we can definitely infer which channel is front left versus front right, right? Same with Amazonics. If we only have one specific channel ordering, then we know exactly how to encode and decode that Amazonics without any metadata whatsoever. But here, we need metadata about where these centroids currently are, right? Where the dynamic speaker locales currently are, in order to reasonably operate on them. So this ends up adding one more interesting wrinkle to our Soundfield problem. And of course, if you want no loss of spatial information whatsoever, you could just not downmix anything, right? If you have 32 sources, we can just save the audio from all 32 of those sources, as well as any spatial metadata that we have, and just retain that in a buffer somewhere. And if a spatial audio solution wants to do that, I don't need to tell them that that's a bad idea, right? Perhaps someone looking at perfmem does, but not me. And finally, I don't have these on our least spatial information to most spatial information slider, but we do have a lot of other intermediate representations, right? If you think about Dolby Atmos, DTS:X, these are kind of opaque bit streams created by proprietary companies that do a really good job of compressing really good representations of sound fields into very little space. The trade-off is that we don't get insight into the actual audio buffers themselves, right? Because these are encoded. So we have to kind of trust Dolby or DTS to carry that audio forward. There's also stuff like MPEG-H, which is great for, multiple Soundfield representations in one, right? You can have an ambisonics bed as well as source positions represented in a single MPEG-H stream because the specification permits that. So that's a bunch of microphone arrays, a bunch of Soundfield representations, a bunch of ways to downmix or, encode audio. But what do we actually get from that? Well, the main thing is that we can't just derive all the spatial audio information that we need from an interleaved float buffer, right? Oftentimes we need stuff like metadata about original object positions, or we need the current rotation of a specific ambisonics bed, right? Or for these dynamic clusters, positions of those dynamic clusters. Furthermore, there's stuff like encoded bit streams that we simply can't represent as an interleaved float buffer, right? These are things that are just opaque byte buffers that we just need to trust, right? And sometimes spatial audio solutions don't want to operate on the amount of channels that we provide for them, right? So they may want more than just a 5.1 output, right? And we can't be authoritative of that because we don't know what the spatial audio solution needs. And the good news is that we came up with a solution. The solution is creating a framework where basically any kind of spatial audio solution can determine whatever kind of intermediate Soundfield representation they want, be it ambisonics, virtual speaker arrays, dynamic clustering, opaque bit streams, et cetera, and expose them simply as submixes in the submix graph, which is where, after 22 minutes, we finally get to Soundfield submixes, right? So this screenshot, it may be a little bit blurry, but this is actually kind of a cool topology that could be created fairly easily, right? So we have the green submix in the upper left corner is just a 2D submix, right? That could have some processing, reverb, etc., using our existing reverb processing that knows how to operate on these 2D submixes. But we can also say, hey, here's an ambisonic submix. And when sources send their audio to that ambisonic submix, it gets encoded to ambisonics using an ambisonics encoder and decoder that Max Hayes actually created and works quite well and is very performant. And then we can send the output of that ambisonics encoding to a resonance submix, right? And what does that mean? Well, that means that we mix that ambisonics bed directly into resonance's internal ambisonics bed. And any sources that are sent directly to resonance, resonance will take care of encoding that ambisonics bed themselves. And then the output of that resonance submix is a binaural stereo stream, which we could then quote-unquote decode, right, to just stereo audio in a normal 2D submix again, which we can do any sort of processing we want. You may notice that we've also plugged in this 2D reverb submix in the upper left corner to the resonance submix. And what happens there is actually that we will essentially treat the individual channels of this 2D submix as virtual speaker locations, which we then send directly to resonance, and resonance can encode that. Of course, this is a very lossy operation. But this also allows us to do things like arbitrary processing to a virtual speaker array that we then can choose to do HRTF processing on if we so choose to do it. I'm trying to avoid specific qualitative design judgments on submix topologies, but of course it's always worth mentioning that dynamics processors, any general nonlinearities that you do after an HRTF processor will actually distort the HRIR and the actual output of the HRTF spatializer itself. So it's worth putting that as close to the end as possible and doing as light dynamics processing post HRTF spatialization as you can. And how do you implement a sound field is a good question. So on the C++ side, when you are creating one of these sort of sound field spatial audio implementations, there's only really two components to it, right? There's an encoder, right, which is essentially when sources get sent to the submix, encode them to our Soundfield representation. And when we need to take that Soundfield representation and output decoded audio to physical speaker locations, we invoke a Soundfield decoder that is implemented by a spatial audio solution, right? So functionally, an encoder stream, all it takes is individual sources with interleaved audio buffers that have some amount of channels, right? And we give them relative transforms and metadata about each of those individual channels. Furthermore, a Soundfield format can also implement custom settings for whatever they want, be it, oh, here's the quality, right, of our spatial audio algorithm. Here's the order of ambisonics we're encoding to, et cetera, et cetera. But the output is kind of whatever you want, right? We have this concept of a quote-unquote Soundfield packet. And that Soundfield packet doesn't need to just have audio in it, right? It can have transforms, the many sources you want. It can have opaque bit streams. I've pronounced opaque/opaque 3 or 4 different times during this talk. I apologize for that. Feel free to tell me the right way to say it after the talk. But we've got this encoder stream, and on the other side, we've got this decoder stream, which is the inverse, right? We've got the Soundfield packet that we've created from the encoders, and we've got the positions of the speakers that we're decoding to. And all we expect from the decoder is finally give us an interleaved audio buffer for these speaker positions. This allows us to also do stuff like define where those speaker positions are for something like an ambisonics decoder or a spatial audio solution. So the only question there is, you may have noticed that we don't have an encode or decode in this connection right here, right? We've got 2 different Soundfield submixes. We've got ambisonics, we've got resonance, and we're connecting ambisonics to resonance. So how does someone implementing a Soundfield format actually control that and implement that? Which is where we create the concept of transcode streams, right? So essentially, you have a factory for your Soundfield format, and whenever somebody tries to plug a Soundfield submix into a different Soundfield submix with a different format, we ask first the input, right? So in that case, ambisonics, hey, for our ambisonics format, can you transcode to resonance? And the ambisonics factory may say, no, I cannot. At which point we ask resonance, hey, can you read ambisonics? To which the resonance Soundfield format in our specific case says, yes, I can do that, and creates a new transcode stream. And transcoder streams just take a Soundfield packet, in this case an ambisonic Soundfield packet, and are just expected to output a Soundfield packet in their specific domain. So this is a case where essentially you plug in an ambisonic submix to a resonance submix. In resonance's case, it reads that ambisonics data and mixes it into its internal ambisonics bed, and we vary over any state resonance needs in the Soundfield packet itself. So the last configuration that we haven't really talked about are external sends, right? We talked about these kind of fire and forget situations where we have a piece of hardware, and once we send audio to it, we never get it back. And that wasn't well expressed previously in our submix graph, but now we have the concept of endpoint submixes and Soundfield endpoint submixes. You see this kind of gray submix here, this node, and you notice that it has an input, but it doesn't have an output. And that's because it doesn't output into our audio engine, right? It outputs to some piece of external hardware. So we have quote unquote 2D endpoints, right? Which you use for stuff like external devices, et cetera, et cetera. But we also have the concept of Soundfield endpoints where essentially any sources or submix output could get sent to this thing, right? Be it ambisonics, and then it will get encoded to that specific Soundfield format and then sent out to some external processor somewhere. It's worth noting that while we do have implementations of Soundfield endpoint submixes that exist, none of them are publicly available right now, as you could imagine. But if you have a problem space where you need something like this, it is supported and is well tested. And actually, the last problem that we need to think about is DSP effects, right? This is a challenge because, we have a whole suite of great submix DSP effects, reverb, tap delays, etc. that work on these 2D submixes, but we don't have the equivalent that just knows how to work on an ambisonics bed, right, et cetera, et cetera. So we have a slightly different interface called Soundfield effects, and they work similarly and from a UX perspective behave almost exactly the same as submix effects normally do. The only difference is under the hood, Soundfield effects operate on a Soundfield packet for a specific format, be it ambisonics, resonance, et cetera, et cetera. So there's none actually implemented in the engine yet. I've mostly just done unit testing with very basic systems like attenuating an ambisonics bed, et cetera, et cetera. But the support is there, and if you ever want to create a new novel approach to ambisonics reverb, test it out, you want to implement an Ambi toolkit, right, in Unreal, the support is there. So that kind of brings us to the future and our future development plans for stuff like this. Obviously, we would like to implement more different types of Soundfield formats, stuff like virtual speaker arrays, dynamic speaker arrays using centroids of clusters of sources. We'd like to implement some Soundfield effects, work on some ambisonic spatial operations that could be dynamically controlled by the game. And I think to get those first two bullet points doable by folks out in the Unreal community, I'll need to write a tutorial. We'll need to write a tutorial for implementing a Soundfield format from scratch. This is kind of half written at this point, so it should come out at some point soon-ish. But in the meantime, we've got some further resources. We've got our current documentation for using Soundfield submixes. Those are available at docs.unrealengine.com. We have our current Soundfield implementations for Ambisonics, Oculus Audio, Google Resonance. Those are available if you sign the EULA and just want to check out our code base. And we've got the actual interface for Soundfield formats in a module called Audio Extensions in Unreal. This says 426, but it's also in 425, I believe. And that concludes the talk. Sorry, that was a very abrupt way to conclude a talk.
Can people hear me? Am I audible?
Yeah. Well, I can hear you.
Yes, you
All right,
are.
cool.
Yeah.
I wanted to say sort of backstory on Ethan as he was giving his presentation. I flashed back to GDC in 2017 when I gave my big talk there to announce the audio renderer. Ethan was in the audience and he asked me if I had ever considered a channel agnostic submix topology. And I was like, yeah, sure. Yeah, we'll do that. And eventually we hired Ethan, and he sort of led the development on this. And it's basically a cool story of young person in the audience actually doing the thing that I said that we would do when they asked if we would do it.
It's been satisfying going from the person frustrated with like the limitations of a framework against like a spatial audio plugin I've been trying to make to designing or helping design also the topology of those frameworks, for sure. Cool.
Dustin, you want to manage the QA session? Or
No, I got
you
it.
have to...
So at this time, we will now be allowing questions. So if you have a question, feel free to use the hand raise emote.
And just to double check, Max and Phil can talk also now, right?
Yeah.
Cool. Awesome.
All right, Aaron, feel free to ask your question.
I was asked to talk, but I'm not Aaron. And I think you've done a fabulous job. It's very good.
Yeah. That's a great question. That was a thank you for asking. It's a fundamental constraint of our previous topology, but going back to this, right? They are essentially just different submixes that exist in the same graph, and all the way on the upper left corner, you can see you can choose format. But because of that, you can have an ambisonic submix and say like a complex virtual speaker array Soundfield submix as just two completely independent submixes that exist, and you send sources to either one of them or both if you so choose. And this is also useful for comparing and contrasting different HRTF spatializers, so we can easily do stuff with this, like, oh, there's an Oculus Soundfield submix versus a Resonance Soundfield submix, and we can send a source dynamically to one versus the other just to do immediate comparisons.
I'd like to take a stab too. Ethan's
Oh, sure.
slides here are on the submix graph, and if you're not familiar with native UE4, there's a whole other implementation path that is not shown here. But essentially, there is sound designer tools to allow them to choose how to send their audio to what submixes. So anytime you play a sound or a sound cue or a group of sounds, and even now at the sound class level, which is a way to group assets of sound assets of different types into sort of a single classification, you can arbitrarily and customarily route your audio to any number of submixes. So the short answer is this is the ultimate quote unquote mix and match of different Soundfield formats and submixes, and it's the truly agnostic way to do spatial audio, where before we would be like, okay, we can mix and match which we thought at the time was very exciting, like a single project might ship on multiple platforms, and each platform would have like, oh, platform over here has Oculus, platform over here uses Google Resonance, this other platform is Steam Audio. But he's saying in the same game, dynamically, even while the player is playing their game, can be rendering all possible Soundfield formats if they wanted. That would be crazy, of course. But like, and the use case for that, as Ethan points out, would be to just do A/B comparisons. So you can say in the same game, this sound is Google Resonance, this sound is Oculus. What does it sound like? I don't know. And this would, in other words, like to compare different spatial qualities, this would allow you to do that sort of thing. Hopefully that answers your question a little bit.
All right. Do we have any more questions?
Oh, sorry, real quick. It looks like some folks were not able to hear the question. But just to have some context for that question, the question was, can you have multiple Soundfield representations that you send sources to in the same game instance at the same time?
Yep.
Okay. We'll restate the question before we answer it in the future.
Yeah.
Apologies.
Anybody else? No?
I can ask a question just to kind of seed the conversation here. So you left out a big hole on ambisonics effects. From my knowledge, there isn't really that many people doing that kind of thing. Ethan, can you articulate some challenges around what it might mean to have a Soundfield submix effect or an ambisonic submix effect?
Yeah, you mean in terms of the practical DSP of doing like a
exactly
ambisonics
like
reverb or
like
something?
why aren't people doing that?
Yeah, well, folks are doing it. Yeah, Earcam for
I mean
a while,
widespread.
but...
I mean mainstream.
Oh, in terms of widespread stuff, yeah, for sure. Yeah, I think it's mostly difficult because they can be computationally expensive in a lot of the kind of naive implementations, right? And I think also just the frameworks haven't been there in game engines in a lot of use cases. But, you can think of a situation where essentially any speaker-specific effect that you create, you could take a ambisonic sped, you can decode it to specific spatial positions, and then operate on those decoded specific spatial positions and re-encode them into your Soundfield bed, right? So that is a common path for a lot of ambisonic CSP effects that they like to do. So for example, you could do something that's kind of a tap delay by decoding from a specific angle in your ambisonic sped and re-encoding in a different position. And now you have taps that are coming in from different spatial places in your tap delay mixing matrix. So that's a common pathway. But yeah, I think it is just expensive. It's a little bit more complicated to grok, I think, for a lot of DSP programmers and effect creators. So yeah, I think that's probably most of why it's not done fairly often in game engines.
From what I've seen, the vast majority of DSP effects are in the DAW context, and the vast majority of those are like stereo. I don't think there's even a lot of multi-channel, like traditional multi-channel bed effects, let alone Soundfield effects. But I think games could probably be a place where some interesting R&D efforts could go, because I think there is a need. I definitely think the future of games is Soundfield rendering, and the whole point of submixes is applying effects to a bed of sounds, and now in this case spatialization, intercoding or transcoding. So I definitely think games are well positioned to be pioneers on mainstreamizing the idea of sound field effects. So people here in the audience, AVAR attracts those types of people. So take that as a challenge. One other question I had, Ethan. A big part of this is endpoints. Can you talk a little bit about endpoints and what that means versus in-graph submix rendering?
Yeah, sure, for sure. So we've got kind of two types of endpoint submixes, and they behave when you select a submix that is an endpoint submix. They behave almost identically to a normal submix. The only difference is they don't have this output pin, right? Because the implication is the output is to some external device, right? So a good application of that is something like, you may have multiple devices and you want to send multiple output rendering devices on your PC, for example, and you want to send specific sources to a specific headset, right, for example, or a voice-specific default voice output. And for a lot of hardware renderers, right, we can send it an ambisonics bed, or we can send it a source to spatialize. And we wanted that to really behave exactly like the way that sound fields work in the engine as is. So under the hood, essentially, it becomes a situation where you just define, oh, here is the sound field format of this endpoint, and we buffer your implemented sound field packet as they come in, as they get encoded, so that you can use them to operate and send audio to, or data, whatever you need to do, to some external API for some hardware device or what have you.
Yeah, a big idea of endpoints is there's a lot of exciting things if you start going deep onto what endpoints imply and what they could mean for games. There's a classic, I want to hear my voice audio on a different device than my game audio, or that kind of a thing. But for installations, you could imagine really interesting aggregate scenarios where there's a ton of different channel configurations in different locations, and you want to have one audio device rendering to those. There's also sort of more mundane things, like maybe controller, like a video game controller has speakers that you might want to route some specific audio to using some game logic. So that kind of a thing. But also maybe an endpoint that's intended to just analyze a mix or monitor a game mix or that kind of a thing.
Yep, for sure.
All right.
Another,
any
yeah, I was gonna say another cool.
questions?
Yeah, I'm just waiting. I'm throwing questions in here to have some kind of conversation. Someone ask Phil and Max a question because they're here for some reason.
I can ask Max a question.
All right, do it.
Max, can you speak a little bit more to the process of ambisonics encoding, decoding, and why? Why do we use ambisonics as a way to express spatial audio in a lot of these systems? What are some advantages to it?
Ambisonic representation is completely decoupled from your output setup. So most audio buffers are one-to-one. If you have a surround buffer, quote unquote, is going to have 5.1, 6 channels or 7 channels, 8 channels of audio. Each one of those channels corresponding to an output speaker, basically. Whereas ambisonics is a mathematical representation. It's a function that we can query. We can say what at this point in time, at this direction in space, is the sound pressure level. And so we can use that to decode ambisonic information to virtual speakers that like Google Resonance uses, which those outputs can then be HRTF'd, or actual speaker arrays. We can literally just instead of it an audio buffer being just a function of time, it's a function of time and angle, both elevation and azimuth. So it's very flexible in that way.
What are some
Nice.
downsides
Okay.
of using ambisonics, Max?
Higher higher order higher order ambisonics can start to get expensive with transformations that we want to apply to them, like the analogy of panning in ambisonics. A sound field would be applying a rotation to that sound field, and those types of operations do scale really quickly with the ambisonics order. And a lower order, while being pretty cheap, has lower spatial resolution. So elements in that sound field, like a bird chirping or something, would appear to be coming from a larger region in space around the user. So it becomes, you can encode as many sounds as you want in an ambisonics bed, and all those transformations and things like that would be constant cost for all those rotations, but the complexity and the CPU usage goes higher as you want a higher spatial resolution, and those formats on disk actually become larger as well.
Oh, looks like we got a question.
Yeah, Megan, go ahead and ask your question.
Well, didn't mean to get on the stage. Sorry.
It's all good.
That's all right.
there
Why don't
we
you
go.
come on
Like,
up?
Every
You can
time I
join us.
click, I just hop onto the stage. So, I did actually have a question. So, like, and I'm still kind of trying to grok the sound field portion of it. But could you pass a mono spatialized source into an ambisonic field, pass it as a parameter, over time, with the submix, or are the submix finite? Like, are they like state based where you are in this submix or you are in that submix? Does that make sense?
Yeah, that's actually a super good question. Well, does someone else want to answer, or I can answer it if needed?
You can answer it.
Sure. Yeah. So the question was, are these submixes kind of entirely state-based and isolated, or can you have, for example, like, oh, we've got a mono submix and that either gets encoded to ambisonics or controls
Mono sound source.
a mono sound source and that gets encoded. Well, do you say a mono sound source or mono submix?
Yeah, so like let's say you have a cave, right? And there's some creature in the cave and you're walking towards the cave, and that's a mono spatialized source. However, as you get close, it suddenly becomes this ambisonic field.
Yeah. Yeah, that's a super great question. So for the mirrored rooms, the use case is you've got a cave, right? And there's a mono source, which is, for example, a creature in that cave, and it is a monaural, and it's very directed. But as you enter that cave and get closer to it, it gets encoded to ambisonics. It might spread out across ambisonics, but it might be more spatialized.
Actually,
Yeah,
Ethan,
go ahead.
I think one thing that from my understanding of your question, Megan, it sounds like there may be, which is totally understandable from the way sound fields are used traditionally in games. But I think you might be confusing the idea of a mono spatialized sound in sound field as if like in a sound field it won't be panned as a single point source, but it would like surround you or envelop you. Like, for example, Oculus supported sound field rendering recently, and they called it a white box for sound, which is a traditional, currently in games, it's very traditional to play like an ambience in a sound field that surrounds you. But
Right.
there's nothing that prevents you from having a pinpoint spatialized sound source that sounds as if it could be mono-panned in a sound field representation. So it's not as if it envelops you necessarily. Does that kind of get at what you're asking it? I mean, one aspect of what you're asking it about, Megan?
Maybe.
So
Well, another example would be like, say, a waterfall that when you're
Yeah.
far away from it, it seems like a point source, but then as you get close to it, that would be a type of asset that you would kind of expect to envelop you. Like that,
True.
that in your
But
authoring, it might include all the bounces around the environment, things like that.
But in both of those cases, it would still be sound field rendered. So you could have it sound pinpoint in sound field is all I'm trying to say.
So you wouldn't have to change, is what you're saying.
Exactly, to get the effect
Okay.
of a point source that then as you get up it envelops you. Sound fields can support that. The other question, which is like sort of a implementation kind of routing question, is like, can I play a sound in let's say it's a looping sound, which would be
Yeah.
like an infinite duration sound. If it's a looping sound out in the world, let's say a waterfall, You could, in UE4, have it render as a traditional panned sound source, in which case that's the normal way that we think about panning. It could be a 7.1 submix or stereo or however you want it. And then in UE4, you can actually route an audio dynamically to send, quote unquote, its audio to arbitrary submixes. So while the life is, so you could actually have it render to a cheaper, I would probably consider this a performance optimization maybe, where you want to limit the number of Soundfield submixes you have for just the sweet stuff that you really want to hear in like a really high resolution. Soundfield will sound better than normal panning if you have a high enough order of Soundfield. So, but you maybe for a set of sounds, you're like, I don't really need to spend the effort encoding to Soundfield on these. But as I get close to it, I want it to get really high res spatialization. You could route audio dynamically based on distance or whatever gain parameter you want to route it to whatever submix you want. Or as Ethan pointed out at one point, kind of threw it away as a concept, you can have sounds render in multiple submixes at once if you wanted for whatever reason. There are plenty of reasons why you would want to do that. Like for example, reverb is a classic case where you render the audio source in like a dry submix, maybe for EQ or dynamics processing, and then you'll send a portion of it to a submix that has reverb. And then that's how you can get sort of distance-based reverb submixing. So it's like the further away you get, the more reverberant it is, because more audio is getting sent to the reverb submix as a function of distance. So, anyways.
Yeah, I think, yeah, in addition to that, yeah, exactly that last point. I think that there's a good novel solution you can create, which is essentially you have a really spatially localizable HRTF render, right?
Yes.
And then you've got a first order ambisonic submix that is, very low spatial resolution, but you can exploit that because it's very performant. It's, very nebulous, and you want it to be kind of intentional that that you can't really localize the specific position of this thing. And you can have the send between either that really localizable HRTF render or that low order ambisonic submix to be dynamic as a function of distance, right? So as you get closer to the cave, we can move into this sort of ambisonic space where we have a reverb on a first order ambisonic submix, and you have your cave interior basically that you were sending to dynamically.
Actually, there's another thing that Megan's question made me realize is this really is a different way of thinking about game submixing. So putting the prior ways of thinking about Soundfield hat on, the way that games often again deal with Soundfield submixes is this sort of white box kind of approach. And another big reason for that is that a lot of our Soundfield rendering is done with assets which have been recorded in Soundfields, like using a Soundfield microphone. Somebody goes out to a forest and puts up a microphone and records a Soundfield, or a 360 video or things like that. That's the sort of normal way of thinking about Soundfields. And we sort of did this talk with the implicit, not explicitly articulated idea that this is sources which are dynamically encoding to Soundfields in the engine, doing their transformations, rotations, and then decoding back out once we hear it in discrete. Like at the end of the day, you're listening on headphones or a speaker system. At some point, it needs to be decoded back into discrete channels. So it's an implicit thing that we're assuming here for this talk, that it's understood that this is encoding and decoding, but we also support just playing Soundfield assets that have been recorded with the Soundfield mic. But but it's really important here to understand that, like, when you have a mono point source out in the world, or even a stereo, however many point sources you have, encoding it to ambisonics, it can rotate, it can move, it'll sound just like a normal pan. It just won't be as terrible. Soundfield rendering with panning just sounds significantly better at higher order. At lower order, it's vaguely better, but not easily identifiable better.
Lawrence, if you want to ask your question now.
So, Aaron, from what you just said,
Yep.
do I understand that from a traditional old school sound design perspective, for a 3D game, you record or somehow produce a bunch of mono sound sources, and you place them in the engine, and then the engine renders that so that you create the illusion of space. Now, right? So, but
think of it as just like a really high resolution pan for a mono source.
Right. For these mono sources, but what you just were clarifying was that if I now take an ambisonic, I've got my awesome Octomic or my second order ambisonics mic
Yep.
now, and I record this beautiful ambisonic sound field out
Yep.
in the forest. And then I put that into your engine.
Yep.
So clarify the point you were making about
Sure.
how that is then behaves, perceived, and I didn't quite catch that explanation.
Yeah. So basically the idea is this is actually kind of a subtle point here. Like you're let's say you have a second order ambisonics recording. What you could do is actually encode mono sound sources into second order, send them to the same submix that your second order source asset is playing in, mix them together in ambisonics, right? So your cool ambient bed is now in ambisonics, and random mono sound sources that you've imported, like your gunshots or footsteps or whatever, encode those to the same ambisonics format, mix them together. Then you have sort of encoded procedurally and dynamically and source audio together in one ambisonics field. Then once that's in the sound graph, submix graph, you can actually transcode it to other formats. You can send it to mix it with like Google Resonance, and Google Resonance has a HRTF to ambisonics format. So then get everything together in one thing, do whatever sound field rotations you need. You could record that. This is a subtle thing we didn't mention, but it's a really cool idea. You could record straight to disk the submix audio that's in that sound field format in a sound field format recorded representation. So like you could imagine a scenario in a game where all of your audio sound field encoded, you record that to disk, the listener then hears it decoded for their local, like say they're wearing stereo headphones or 7.1 or whatever, but you have a sound field representation on disk, and someday in the future you may want to hear that recording on a different output endpoint. And so you'll have all of the spatial information saved for the posterity. Another use case too is pixel streaming, which is like a huge thing in gaming right now, where games are played on a server, right? But what endpoint are people listening to? Does the server know? Who knows? What about Twitch streaming? Let's say in the future, Twitch streaming has some API where we could feed it a sound field rendered submix, and then each of the individual users can hear it however they want on whatever endpoint they have. So there's just a lot of crazy use cases, and it's a mix and match kind of a thing. So it's extremely flexible.
Very cool. Thank you.
One interesting application, for example, is what I would call spatial submixing. This is a thing that we kind of support already in UE4 with what are called source buses. One crazy idea is to do a transcoding to a virtual speaker array in engine, then re-encode it back into Soundfield. So for example, you could have a Soundfield submix where all your really cool Soundfield ambiences are recorded that you've imported into the engine, your in-rendered sound sources. Go put those into a Soundfield submix, and then send that audio to a source maybe that represents some location in space that's a mono source. Then put that back, for example, you can imagine like an outdoor ambience as you walk into an indoor part of a room. Then you could basically decode your sound field as if it's coming from one of the windows, render that in engine as a mono sound source, encode it back into Soundfield to get that high resolution audio, and then hear that out on your endpoints. So there's always at some point a decode into some output representation. But there's once you start thinking about the idea of this sort of sound field, some interesting use cases come to mind just like that.
Hey, Aaron, I think maybe what we should do now is reconvene in the AVAR lobby. And will you, Aaron, and your team be able to join us there for a few more minutes in case people want to ask more questions? Can I ask for another round of applause for this awesome team and their amazing presentation? I just think they're the best. Yeah, woohoo! Really cool. You guys, Ethan, Aaron, Max, and Phil, thank you so much. Let's, you guys all know how to go to your events, My Events menu, and go to the AVAR lobby. We'll go hang out. You can see we hung some hung my new banner up in the lobby, so you can tell me how you like it. And there's also the schedule for the Monday schedule for the conference posted in there. You can tell me if you can read it or not. I know we have a bunch of different devices. So let's all head over to the AVAR lobby and see you there.